So we're very happy to have David Ricciche from Princeton and the IS at the moment. And so his background is in doing
simulations
like this one you showed here. And so today he will be talking about that and what they actually can tell us.
Okay, thank you very much for having me here, and thank you for coming here now. Today I'm going to talk about multi-messenger astrophysics with numerical relativity. As you can probably guess from my cover slide here, the bulk of my talk will be dedicated to neutron star mergers, which is a kind of hot topic now for multi-messenger astronomy. But we'll also talk a little bit about core collapse supernovae towards the end of my presentation. So let me start by explaining what I mean by multi-messenger astrophysics. By this, I mean just a study of astrophysical objects by means of multi-messenger observation. For example, neutrinos and photons, as was the case for supernova 1987A, which was a kind of preview to what multi-messenger astronomy was going to be and is going to be in the next few years. So the kind of sources that we are after are compact binary mergers like neutron star, neutron star, neutron star black hole, perhaps even black hole mergers, and core collapse supernovae. What all of these events have in common is that they are extremely violent. They produce abundant gravitational, neutrino, electromagnetic radiation, so that we have a chance to detect them with current technology in all of these channels, or at least in some of these channels. Multi-messenger observation probably really started very recently with this famous detection of a pair of merging neutron stars by LIGO and by its electromagnetic observer partners. So as I'm sure you are very well aware, on August 17, there was a gravitational wave signal detected in the LIGO Virgo detector network. The signal lasted about 2 minutes. Which corresponds to almost 2,000 orbits of this binary. Shortly after the time when these two objects came into contact, about 2 seconds later, a gamma ray flash was observed by both the Fermi and the integral satellites in a region of the sky that's coincident with the sky position as inferred from the gravitational wave signal. Afterward, the same system was detected in the UV, optical, infrared, X-ray, and radio bands. So this is probably one of the best observed transients ever, as well as being the first transient for which we have both gravitational waves and photons detected. So a big part of my talk today will be reviewing these observations, explaining why they are important and why we are learning a lot about neutron stars and compact objects from these observations and why we think we will learn even more. But I also want to point out that modeling and understanding these observations is a real challenge for us theorists. Because it's one thing to separately model emissions in different channels, but it's another thing to have models that can predict simultaneously from first principles, gravitational waves, neutrino, and photons from a system. And today I'm going to claim that numerical relativity is perhaps the only tool that can really do this, that can really predict at the same time all of these observables. So what is numerical relativity in one slide? Numerical relativity is simply solving Einstein equations on a computer. Einstein equations tell us how the geometry of space-time evolves and how matter and radiation within the space-time move. So with numerical relativity, what we do is we take a space-time and we slice it into things that we call constant time surfaces or hypersurfaces. We prescribe initial data on one of these slices, for example, initial data describing 2 neutron stars shortly before they collide, and we evolve it in time. The key ingredient in all of this is that you need large computational resources to perform these simulations. These are really computationally intensive. However, thanks to the fact that computational resources and high-performance computing has been growing very rapidly in the past few years, we are now at the point where we can not only predict gravitational wave signals by doing these simulations, but we can include enough microphysics to start predicting also other things, for example, neutrino signatures or electromagnetic signatures. Most of the simulations I'm going to present today were performed using this code that's called Whiskey THC. This is the code that I originally developed as part of my graduate studies. I want to advertise it a little bit because it's open source. You can just go to this web page and download, and it comes with everything needed to perform neutron star merger simulations. It's based on a collection of open source software called Einstein Toolkit. The Einstein Toolkit comes with code to solve for the metric of space-time, to find event horizons in simulations, to extract gravitational waves from numerical spacetimes and things like that. And what WSGI THC adds on top is the description of neutron star matter. So it solves the equations of generativistic hydrodynamics. And it has also a treatment for neutrino radiation, which is still not as sophisticated as I would have liked it to be. If you're curious about the name, THC stands for Templated Hydrodynamics Code. And WSGI is the name of a legacy code from which I started developing everything. As an example of one of the simulations I performed, I show you a simulation of a binary merger. These are two neutron stars, equal mass, in this case 1.4 solar masses. And what you're going to see is the last 4.5 orbits or so before merger and the post-merger evolution. The color code here is density. You see yellow and thick is high density, which for us means 10 to 13 grams per cubic centimeter. And everything that's transparent here is matter below 10 to 9 grams per cubic centimeter, which for us is low density. So in our typical simulations, we search just few orbits before merger because this is really the part of the evolution where you need numerical simulations to understand what is happening. You see that eventually the stars come into contact because they have radiated away their angular momentum, and they form this object at the center, which we call hypermassive neutron star. This object is stable only because it has a large amount of angular momentum. But eventually, in this simulation, it radiates angular momentum away in gravitational waves and collapses to form a black hole surrounded by a thick accretion disk. So this is what happens in this simulation. Just to give you an idea, the full physical time here that we have simulated is about 20 milliseconds. And this simulation took about 2 weeks on 200 cores. In general, the outcome of neutron-star merger can vary depending on the mass of the system as well as on the yet still unknown equation of state of neutron stars. So if the total mass of the system is small compared to the maximum mass of a neutron star, then what happens is that you can form a stable remnant, or at least something that survives for a very long time. If instead you have a very massive system, you form a black hole immediately without passing through this intermediate phase with a hypermassive neutron star. What happens in this case is that an event horizon basically forms at this point when the two stars are colliding. An overdensity is formed here, and everything falls inside of the black hole. And you're left with a black hole in vacuum. And everything in between is also possible and not excluded. Neutron star mergers are definitely not shy about advertising themselves to the rest of the universe. Indeed, they are very loud gravitational wave signals, and they are bright throughout the entire electromagnetic spectrum. I like this picture because it gives an idea of what the theory was shortly before the detection actually happened. This picture was made before the detection. Already at that time, there was strong substantial evidence linking neutron star mergers with gamma ray burst, although there was not really a definitive proof. And one of the main channels by which neutron star mergers were expected to be bright was in the optical and infrared counterpart. The reason for that is that there is material being ejected during the time of the merger. This is material that's radioactive, and the radioactive decay of this material was expected to produce radiation in the optical and infrared bands. Neutron star mergers were also anticipated to be loud in the radio bands, and there were many other mechanisms proposed to make neutron star mergers shine, and I'm not going to discuss all of this. So this was the theory. Then what happened with the actual observation? So the real star of the show is for sure a gravitational wave signal that was detected by LIGO. I'm not going to say too much about this because I know that the LIGO team here at CITA was directly involved in this detection. So I invite you to talk with them and ask them any questions if you haven't done so already. The one thing that I would like to emphasize is that it's only thanks to gravitational waves that we know anything at all about this source. Because it's thanks to gravitational waves that we know the masses and the orbital parameters of these objects. Otherwise, we would have just seen a blimp in the infrared, something else in the gamma ray, and we would have had no clue of what was going on. And so these are the results that LIGO published for the masses of the two objects that we think are neutron stars. And as you can see, there is one quantity that's very well constrained. This particular combination of the two masses, that sometimes is called chirp mass, is constrained to be in a very thin region around this curve. The total mass of the system is also very well constrained, especially if you assume that the two neutron stars had a small spin, while otherwise the total mass is more uncertain, while the mass ratio is not as well constrained, especially if you allow for large neutron star spins. As I was already mentioning, the optical and infrared counterpart was the most anticipated counterpart, and indeed it was detected by several teams already 11 hours after the merger itself. This is the observation from the dark energy camera team, but a number of other teams were involved, and they all found the counterpart here, and here is already faded at this point in time. So the reason why this counterpart was so much anticipated and there was so much enthusiasm for it is because this is linked with the problem of the origin of heavy elements. As you probably know already, only hydrogen, helium, maybe a little bit of lithium, and a few other elements were produced immediately at the time of the Big Bang by Big Bang nucleosynthesis, while all other elements that form our body and we see around us have been formed in astrophysical processes. They could be inside of massive stars by gamma rays. A large fraction of the elements heavier than iron in particular is formed by a so-called R process, which is rapid neutron capture process. For this process to operate, what you need is a small seed nucleus capturing neutrons to grow and form a large nucleus. The conditions needed to produce this process are very extreme because you need a large excess of free neutrons. So from the very first time this process was proposed more than 50 years ago, there was a problem of what was the astrophysical environment that could provide these conditions necessary in order to produce these elements. And these include elements like gold or platinum. Europium is another element produced by the R process. For a long time, core collapse supernovae were commonly thought as being the environment producing the right condition from the R process. However, in the past few years, observations of metal poor stars, observations of abundances of radioactive isotopes in the solar system and in deep crust deposit in the sea, as well as a failure from theoretical models to produce the right condition for the R process, are starting to point out that core collapse supernova cannot be responsible for a large fraction of the R process elements, especially not for the most heavy elements like gold. Magnetorotational instability supernovae, so supernovae with a jet engine, are still not excluded, but at this point, the real most of the interest is in neutron star merger, and the reason is, of course, that the optical counterpart that we have observed for GW170817 is consistent with the radioactive decay of byproducts of the R process. So all of the attention is now on neutron star mergers. One thing about the counterpart that was predicted but not really anticipated is that it had multiple components. And I think this is nicely shown in this figure I took from this paper by Cooper, Wife, and collaborators. Here you see the light curve from this Kir Anova event in different bands, as well as theoretical fits. These are all single component fits. And you can see that you can try many different things, but it's very difficult to fit at the same time the early optical UV data and the late time infrared data. If you fit one, you typically misfit the other. More recently, some models have been proposed that can fit both, but then you really need to really fine-tune the composition and the velocity distribution of the outflow if you want to explain everything. Instead, the most natural explanation seems to be that there was more than one outflow component. In this case, you see that with a two-component model, you can easily explain both the early time data and the late time data. So you have one component that shines at early times and then becomes invisible, and another component picks up and shines in the infrared. I think these multi-component models are favored on theoretical background because it was already anticipated that neutron star mergers would produce different types of outflow. And the reason comes from calculations of R process nucleosynthesis using nuclear reactor networks. So if you start from a first principle calculation of what happens to a packet of material as it's decompressed, in the conditions typical for neutron star merger outflow, there are basically two possible outcomes. If the material is very neutron rich to begin with, which is something that we typically parameterize in terms of the lepton fraction or proton fraction of the material, so if this material is 1% made of protons and everything else is neutrons, then the R process proceeds and you form all of the heavy elements, including elements in this region here of the third peak and second peak. This is the relative abundances of elements. These red dots are the solar abundances. If instead you increase the proton fraction a little bit, at some point you hit a threshold around the electron function of 0.2 or so, where you stop producing these elements. Instead, the R process runs out of free neutrons before it has a chance to form these heavy elements. This is important because if you don't form elements in this region here, there are lanthanoids and actinoids here, then the opacity of the material changes by orders of magnitude. So even adding a 2% composition in mass of lanthanoids is able to change the opacity of the material by more than 2 orders of magnitude. So what this means is that if you have lanthanoids or actinoids or both in your outflow, then you can trap radiation for much longer. And radiation only escapes at very late time when the material has had time to cool down, and everything comes out in the infrared over a week time scale or so. Otherwise, radiation comes out at earlier times, so the color is bluer because it comes from material that's still hot. So the fact that you have these two possible outcomes suggests that there should be two components to the Kir Anova. And this is also what we find in simulations after all. This is a snapshot of one of my simulations. Here you see density and composition in the meridional plane. So here at the center is the merger remnant, and the eject is flying out in all directions. We know from simulations that there are many components of the outflow. So there is a component, for example, that's tidally ejected. So it's just the tidal tail of the two neutron stars. This material accelerated shortly before merger that leaves from the system close to the equatorial plane. This material is typically very neutron rich. So here is blue is very neutron rich. And this is material that if ejected would give rise to the red component of the Kir Anova. So be careful because color coding here is a bit weird. While high latitude material is typically reprocessed by neutrino radiation. So all of this material here has absorbed a lot of neutrinos, had their lepton fraction increase because you absorb electron neutrinos onto neutrons and you form protons. This red material, if it becomes unbound, this would give rise to the blue component of the Kir Anova. So the color scheme is a bit inverted, but the reason why I like it this way is that this material is hot. So it's more intuitive to plot it red, although, of course, when observed, this will shine in the optical UV, and this will shine in the infrared.
So the neutrinos are driving it as well?
The neutrinos are also driving it. If you don't include neutrino heating, you don't have any outflow at high latitude, actually. So what we have done is actually we have gone one step beyond, and we have taken output from simulation and created our own Kir Anova model. So what we took from simulations are things like, for example, the angular distribution of the ejecta, how much mass is ejected as a function of angle, as well as the composition. We have included different components of the outflow and so on. And we can either use this model to predict the light curve given a simulation, or do the other way around and try to fit observations by having some of these parameters as fitting parameters. And if you fit a light curve like this, indeed you can fit very well both the optical and the infrared data. And of course, this is something that many other groups have done also before us. So for us, the real reason why we did this experiment is not that we want to repeat the feat that other people have more expertise in doing. Is that this allowed us to create the first model that really can connect simulations with observations. And another reason why this model was innovative is that it's also the first model that has a clear angular dependence. So you can place a weak constraint on the observation angle from the optical data. So what we find is that about 5% of material was ejected, possibly more because it's easy to hide material behind the rest of the Kir Anova ejecta, so material that become transparent only at very late times when the radiation is already redshifted too much in the infrared. If you take this number at its face value and you combine it with the event rate as inferred from LIGO, and if you assume that all of the ejecta has a composition similar to that of the R-process elements in the sun, then you can explain all of the heavy elements in the universe just with neutron star mergers. However, be careful because we don't have really a direct proof that gold was produced in this event. We have proved that there were some lanthanoids in the outflow, and we know from theory that it's very difficult to produce lanthanoids and not to produce gold. But nevertheless, it's important to remark that there is this subtlety.
This 0.05 solar masses, did that come out of simulation?
No, this comes from fitting the data.
In your simulations, can you make a prediction?
So in the simulations, there are many different components of the outflow. Some of these are under control in simulation, and we can simulate it. So there are part of the outflow that comes immediately out at the time of merger.
That's more like 0.01.
Yes. However, much of this outflow will probably come out at late times that we cannot currently simulate in full numerical relativity. So other groups have instead done the opposite direction. So they have started from a post-merger configuration, idealized, and looked at how much of the disk is unbound. So we think that a combination of these two components of the outflow is what made this 0.05. Probably most of the blue component of the outflow was either dynamical ejecta because of the high velocity, or was maybe accelerated by magnetic fields, as was recently proposed, so a magnetized wind. So what have we learned about neutron stars from all of this? One of the reasons I was personally very excited about LIGO detecting neutron stars is that neutron stars offer us perhaps the only way to learn about matter at extreme densities, because we know for sure that neutron stars have to have a density larger than that of the atomic nucleus, because otherwise they wouldn't even form at the time of core collapse. You need to reach sufficiently high density for the repulsive component of the strong nuclear forces to kick in order to form the neutron star in the first place. So we don't know exactly what is happening in their core, whether they are formed just by nucleons, whether there are more exotic particles, what are the properties of this material. So to zero further, what we are after is the equation of state of neutron stars, that is a relation linking pressure and density inside of neutron star. If we had this relation, we could just solve the stellar structure equation and compute masses and radii of neutron stars. But unfortunately, we don't have the equation of state. What we can try to do instead is invert the problem. If we have masses and radii of neutron stars, or equivalently masses and, for example, tidal deformabilities of neutron stars, you can invert this problem and recover the equation of state. And this would be a first step towards understanding what's happening inside of the core of neutron stars. The way that LIGO can do this is by measuring tidal effects. So neutron stars are not point particles. They deform in each other's tidal field. And if you were to sit here on top of this neutron star, since the neutron stars are not co-rotating, you would see a time-changing quadrupole as the tidal bulge goes around the neutron star. So this is yet another source of gravitational waves. So because of the tidal deformation, neutron stars in spiral slightly faster than 2-point particles or two black holes would do. So the effect of tides is encoded in the phase evolution of the gravitational wave signal, which is something that LIGO can measure exquisitely well.
Doesn't this depend also on the spin of which neutrons are, rather than just the orbital momentum?
So to linear order, what we are after is the tidal law of number, which is just a proportionality constant between the deformation of the neutron star and the tidal field from the companion. So the evolution of the system then depends on many things, including the spin and so on. But if you assume that you know the spin of the system, then you can measure this quantity. Or in other words, let me explain this perhaps a little bit better. The spin enters inside of the phase evolution equation with some power of the post-Newtonian expansion parameter, so some power of the orbital frequency. The tidal deformability enters with another power. So in principle, the two are distinguishable. Of course, life is not as easy as that, because you can easily mimic the effect of tides with spin. So I think it's actually more difficult than it looks like to measure this quantity. But at least theoretically, it is possible. And in all of this, when people talk about this tidal law of number, this is all linear theory. So this tidal law of number doesn't know anything about spin. There is no nonlinear theory of tides in GR, as far as I know. So what we are after is a constraint on this quantity. Actually, the way it enters into the phase evolution is through this combination between this proportionality constant and the mass of the star to the 5th power, which is sometimes called the dimensionless tidal parameter. And this is what LIGO has measured. These are posterior probability distribution for these parameters, lambda 1 and lambda 2. So the tidal deformability of the 2 neutron stars. This is the posterior, assuming a high spin for the neutron star. This is the posterior in which the spin is not allowed to be large. Overall, the constraint is that there is a strong constraint on this quantity. It's a weighted combination of the two tidal deformabilities that is constrained to be less than 800. This is a dimensionless quantity to 90% confidence level. So this is what the gravitational wave data alone says. So the question we asked ourselves is whether we can say something more by combining this with electromagnetic observations. And the answer is, we think yes, by using simulations. So this is how we did it. So we performed a large set of simulations. And for each simulation, we looked at the tidal loft number, this lambda tilde quantity, which is dimensionless. And we computed the final disk mass plus the ejecta mass. So this is an upper bound to what you can eject after merge. Because, for example, this binary has a black hole with a torus of 10 to minus 3 solar masses. Even if all of the torus is unbound, this is orders of magnitude below what we know is the ejecta mass from the observations. So this model is ruled out as being compatible with GW170817. It turns out that there is actually a very nice dependency of this disk mass plus ejecta mass, as well as the black hole formation time on this quantity. And the reason is that this dimensionless quantity is basically the compactness of the 2 neutron stars, because this depends weakly on specifics of the equation of state and then scales with the 5th power of the compactness. So in order to make this lambda tilde small, you have to start with very compact stars to begin with. So these are already very close to the collapse to black hole threshold. So when the 2 neutron stars come into contact, the black hole forms immediately and there is no ejecta, no nothing. So these models can be ruled out. So on the basis of this simulation, we can place a complementary constraint on the tidal deformability of neutron stars. So what LIGO says is this number has to be less than 800 to 90% level. And we can say that it has to be larger than about 400. Of course, we need more simulation to say whether this is 90% or 50% confidence. But the way I visualize it here is that if you fix the equation of state, for example, you assume that the equation of state is LS220, one possible equation of state, then this tidal parameter depends on two things, a shear mass, which we know exquisitely well, and the mass ratio. So in this plane, it's just a curve. And you can check whether this curve enters the forbidden region or not. And on the basis of this, you can say that this equation of state is disfavored or consistent with the data. So now in the sure.
When you say equation of state, you mean just the response of pressure as they change the density?
Yes, that is correct.
Wouldn't this also depend on viscosity? Because this would determine the strength of the tidal interaction between the 2 neutron stars.
So in the theory that we're using here, the viscosity is really not important, because the viscosity in neutron stars is very small, so we don't think neutron stars will be co-rotating. And the mechanism for dissipation is gravitational waves, it's not viscosity. So there is a torque due to the fact that the tidal bulge is not pointing to the other star, but this is not due to viscosity. It's due to GR effects, and the other reason why you lose orbital angular momentum is because you're emitting gravitational waves. So if you see it on the neutron star, you will see a time-changing quadrupole. It's not the same as, I don't know, white dwarfs, where viscosity would be more important. So in all of this theory, we didn't include any viscosity. And the simulations don't have explicit viscosity.
So
of course, there should be some, but
linear deformation doesn't change the volume, right? You compress on one side, you stretch it on the other side. So if the volume doesn't change, then why should the equation of state matter?
So the tides are not exactly incompressible. So there is a bit of that dependency on the equation of state. But the main way in which this enters the equation of state is the compactness. So if the star is very compact, then it's very difficult for it to be deformed.
So it only matters on the initial
So-
distribution of...
Yes, so to linear order, if you assume that the tides are incompressible, indeed this is just a compactness. In practice, there is a small dependence also on the equation of state because it's compressible. But, okay, now I will, sure.
Makes it all interesting if you put them in the more usual case where you also add the total mass and so on, that we know that two solar mass neutron star has to exist, or is this still, is it sort of, in principle this is nice, but actually all the equations of state that were still allowed are sort of in this regime anyway?
I think this equation of state, FPS, it was already rolled out, but the other ones, as far as I know, they are all allowed. The ones that I plot here, H4 is still allowed.
Well, it's now not allowed anymore, I guess, from the gravitational waves.
Yes, here the constraint is a bit weaker if you look at the lambda 1, lambda 2 separately. But here it seems to be inconsistent with the equation at 90% confidence level. So it's not excluded that you're in the 10% case.
But the 800 limit from the gravitational waves is assuming small spins.
It's assuming smaller spin. On the paper, there is a quote saying that with large spin the limit is 700, which I don't understand, to be honest. I was going to ask you. But yes, the 800 is for small spin. So in the last part of my talk, I will talk about two possible future applications of gravitational wave astronomy that are very close to my heart. One is the detection of the post-merger. And the reason why I think detecting the post-merger would be really exciting, that this would be the way really to say what happens after merger, whether a neutron star survives for long or not. But also in general, because this would be the only way to prove the equation of state at the really highest densities. Because one limitation or one possible worry that I have is that most binaries we know of, neutron star binaries, have masses very tightly packed around 1.35. While there are neutron stars that are at least as massive as 2 solar masses, possibly more. So if we want to learn about those neutron stars, we cannot do so by looking at the 1.35 neutron star solar mass, because there could be a phase transition at high density and we would not know about it. So the question that we asked ourselves was whether it is possible to then measure such change in the equation of state at high density by looking at the post-merger. So we have taken two equations of state that are identical at low density. These are called DD2 and BHB lambda phi. They're basically the same equation of state, but this equation of state also has hyperons appearing at high density. So according to this equation of state, a new degree of freedom appears inside of the neutron star. This reduces the degeneracy pressure of neutrons, so the equation of state is a bit softer. So you can see here is a diagram of mass versus central density. If you include hyperons, you reach a smaller maximum mass, and the star is also more centrally condensed. So the question we asked ourselves is, can we distinguish these two starting from binaries that live here? And the answer is yes again. Here I show visualization. This time now is the meridional plane, sorry, the equatorial plane, and this is density color code. Here is the case with the hyperons, so a kind of very soft phase transition, and this is the standard equation of state. So of course, during the in-spiral, you can really not tell apart these two systems because they have the same equation of state. And then things start to change after merger, because in one case, the density becomes larger, you form a more compact and bound remnant, while in this case, you don't. The remnant stays larger. You can see it also in this plot here. Here show the central density as a function of time from merger. For these two, the blue line is the case with hyperons. The red one is no hyperons, so standard equation of state, and this is the binding energy. So what is happening is you form new particles inside of the neutron star. The equation of state softens, so the star contracts. For it to be more compact, it has also to be more bound. So the binding energy is larger in absolute value. And now, since energy is conserved, the difference in energy between these two binaries has to go somewhere, and it will go in gravitational waves. So the gravitational wave signal has to be different between these two binaries. There is no way around this. And indeed, it is different. If you look at, this is the strain signal as a function of time. The blue line is, again, BHB lambda phi, so the case with hyperons. And the red line is without hyperons, so the standard case. You can see here the strain. This is the time of merger. You cannot distinguish these two during before merger, but you can after merger. This is the time frequency spectrum of the two signals. We find that these two have roughly the same peak frequency after merger, so you cannot tell them apart by looking at the peak frequency. But the time evolution of the strength of the signal is different. So in this case, you radiate much less energy, while in this case, you radiate more energy. Not only the amount of energy radiated is different, but there is also an amplitude modulation of the signals. So the frequency content of these two signals is different. Yes?
It seems like in transitioning from normal matter to strange matter, you would also, in principle, emit a lot of neutrinos as part of the plate
Yes.
changing reactions. So it's not clear that some of that energy budget isn't just carried away in a large amount of neutrinos. How much neutrinos are emitted during these kinds of transitions?
So the neutrinos are also emitted during, neutrinos were included in this simulation. The problem is this phase transition happens deep inside of the neutron star, and the cooling time scale is of the order of a second. So it's true that theoretically, you can radiate this difference in neutrinos, but actually it turns out that it's radiated very fast, very rapidly. Yes, neutrinos are trapped. Otherwise, the binary with BHB lambda phi would stay inflated for a long time until it has the chance to radiate away neutrinos. And we have looked at the distinguishability between these two equations of state. So what I plot here is the bias factor. So you can think that a bias factor of 10 or large is kind of a 5 sigma detection, roughly speaking. So what we have looked at is how far you can tell these two equations of state apart in this very idealized scenario where there are only two equations of state and one is the right equation of state of nature, which is not clearly entirely realistic. However, we find that with advanced LIGO, you can perhaps say something interesting already for binaries 20 megaparsec or so if they're optimally oriented. But things start to become really interesting with next generation detectors, where you will be able to see these things with high significance to 100 megaparsec or more. And I just want to point out that there are binaries that merge close by, so it's not completely crazy. One caveat, or one thing that I didn't mention explicitly before, is that in our analysis, we did not assume that we have the capability of measuring how much energy is radiating gravitational waves. We just renormalized everything so that the two signals have the same signal-to-noise ratio, and we looked at the mismatch. But very recently, two things have happened. First of all, the LIGO team has been really good at doing amplitude calibration, much better than we thought it was possible. And the second thing is that data analysis techniques have been developed that can also constrain the total energy emitted, and these were developed here at CITA. So I think that with this in mind, the prospect of learning about the equation of state from the post-merger and about phase transition at high densities are really bright. And one possible thing to worry about is that in the post-merger there is a lot of physics going on. Not all of it is captured in our simulations yet. One is finite temperature effects and neutrino radiation. We have something to treat neutrinos in our simulation, but still just the first order approximation. We have to do better there. But one thing that we really worry about is MHD instabilities in the post-merger phase, because these are expected and known to operate, but at scales that are unresolvable because they operate at scales of a few centimeters or less. This is the scale of the MRI, of the fastest growing mode of the MRI inside of the hypermass neutron star. So we cannot resolve this scale, but we can try to parameterize our ignorance and look at the effect of turbulence in the post-merger. And this is what I have done very recently using a simulation technique known as large eddy simulations. So the idea here is we introduce an extra term in the equations that mimic angular momentum transport. We parameterize this angular momentum transport with a length scale. We take 0 to be the default value, so what everyone has done so far. And then we change this value from 5 to 50. 50 meters is a value that I consider to be large for the core of the hypermass neutron star. You can think of this length as being the characteristic length or the characteristic size of turbulent eddies inside of the merger remnant. So what happens when you change this quantity? One good news is that the gravitational wave peak frequency doesn't change. So you can really hit the hypermassive neutron star very hard, change its structure significantly, but you still get the same peak frequency for the gravitational wave signal. So this is good news because a lot of literature studied the post-merger peak frequency and what we can learn from it, and now we have shown that it is robust. The amplitude of the signal, on the other hand, can depend on the amount of turbulent dissipation that you have, simply because you transport angular momentum. So for small values, the dependency is small. Of course, for large values, the dependency is large. So the next question will be to understand what is the right value for this mixing length. For this, we will need to perform either very high resolution MHD simulations or probably something like a local or semi-local simulation setup. In the very last part of my talk, I will talk about another future perspective, which is detecting gravitational waves, neutrinos, and photons from core collapse supernovae. Because if you ask me, I would claim that this is the next major discovery that LIGO could make. And I would try to explain why I think this is really exciting. So before I get into that, let me briefly remind you what the explosion mechanism of core collapse supernovae is, just to set the stage. So core collapse supernovae is the violent explosion of a star, a massive star, at the end of their life. Here is an example of a massive star nearby. And all of the action happens in the core. Massive stars go through all of the advanced burning stages. In particular, at the end, they start to burn silicon. Silicon burning lasts only a few days before you run out of fuel and you create a massive iron core. Since iron has the largest binding energy among the elements, nuclear fusion of iron is not energetically favorable. So the iron core just sits there and supported against collapse by the degeneracy pressure of electrons. Eventually, you burn enough silicon that the iron core becomes larger than Chandrasekhar mass, and then it collapses. Collapses dynamically from an initial radius of 1,500 kilometers or so down to a radius of 50 kilometers in about 200 milliseconds or so. At some point, the density inside of the core becomes larger than nuclear density. And then the equation of state stiffens all of a sudden. So the inner core stops its collapse. It forms what we call proto-neutron stars, something that will become a neutron star. The outer part of the core is in falling supersonically. So it doesn't know that the inner part of the core has stopped collapsing. So it rams into it. And the result is that it produces a very strong shock wave. The shock wave travels outwards, but it's dissociating heavy nuclei. There is a lot of neutrino losses behind. So eventually the shock wave stalls. This takes about 50 milliseconds, perhaps, for the shock wave to stall. And then something has to happen to revive the shock wave to trigger an explosion. And this is the part of the theory that still needs to be completely understood. If the explosion is successful, then the shock wave runs out. It takes 12 hours, maybe a day, for the shock wave to travel through the star. And only when the shock wave reaches the surface, photons can freely escape and we see them. And the proto-neutron star meanwhile cools down, emitting neutrinos for about a minute. So where do gravitational waves come into play in all of this? Here there's no binary, nothing that obviously is emitting gravitational waves. So gravitational waves come from the proto-neutron star itself. And now we show a visualization of one of my simulations that explains what happens. So here you're going to see a 2D simulation. This is the entropy in the XZ plane. This is neutrino luminosity and average energy from our simulation. So this is the time of bounce. At this time, the proto-neutron star is formed, is contracting because it's emitting neutrinos. These are density contours. What happens is that the region around the neutron star is unstable to convection because there is neutrino radiation heating up the material. And there are bubbles hitting the proto-neutron star. There are bubbles and plumes, and when the proto-neutron star is hit, it vibrates. And it's this vibration that produces the gravitational wave signal. And this simulation goes on for a bit now. At this point, the star has already exploded in this model. You don't see it on this scale, but there is still accretion from fallback material. So gravitational wave keep on is emitted for a long time. So if you look at the gravitational wave signal from a core collapse supernovae, it looks something like this. There are a number of bursts. These are times when there is a particularly massive plume hitting the proton-neutron star, and then the proton-neutron star vibrates. There is, if you look at the time when the star explodes, this is entropy in the z direction. There is a kind of trend. This is just a linear memory that develops, but this is undetectable. But overall, the signal just looks like white noise. So for a long time, I was very skeptical that LIGO could detect anything like this because it looks like noise.
This is just from a 2D simulation?
This is from a 2D simulation. From a 3D simulation, the signal actually looks identical. So the only thing that changes is the amplitude of these plumes, because these are stochastic.
Usually when you do simulations in 2 and 3D, in 3D you get the spectrum tends to put more energy in high wavelength.
That is correct.
Low wavelength.
Yes.
And this, it seems to me that this would suppress the noise because it would give more energy to higher moments, not the quadruple moments, but even to higher, which decay faster.
Yeah, that is correct. So what happens in 3D is the bubbles of convection around the proton-neutron star are smaller. So they hit the surface with less energy. So the overall amplitude is maybe a factor of, I don't know, 2 smaller. This is debated because there aren't that many 3D simulations. However, the overall qualitative picture is really the same.
Another point is that there is some constraint on the symmetry of the explosion, both from polarization of supernova remnants and from kicks of neutron stars.
Yes.
And the question is are these results consistent with these two observations?
So we haven't, okay, in 2D, I think you cannot really say anything about the asymmetry of the explosion because as you have pointed out, in 2D you tend to funnel energy to large scale. So 2D simulations are not the right tool to predict this. So the asymmetry of the explosion would enter in the linear memory part of the gravitational wave signal that I don't think is detectable. So what we see here is just the vibration of the neutrons of the proton-neutron star as it's hit by plumes falling down. So what changes from 2D to 3D is just the strength and the type of heating that you do on the proton-neutron star. But then the way in which the proton-neutron star vibrates is very consistent between 2D and 3D models. We have not done 3D version of this simulation, but other groups have done 2D and 3D and compared. But so the point I was going to make is that this looks like noise, but actually it's not noise. So since the gravitational wave signal is in the audio band frequency, I made a sound version of this gravitational wave. So let me play it again. To me, it doesn't sound like noise at all. There is clearly a frequency, a characteristic frequency. Indeed, if you do the Fourier decomposition and plot the spectrogram, it's not noise, especially at late times. There is a clear chirp-like signal. So there is a signal that grows in frequency with time. For a long time, people have tried to understand what is the exact origin of this signal. And the current interpretation is that it's due to gravity modes, not gravitational waves, but gravity waves inside of the proton-neutron star. And very recently, with Victoria Morozov, a postdoc at Princeton, we have done a systematic analysis of this. So what we have done is we have extracted the proton-neutron star profiles from our simulation, and she did a perturbation analysis. So this is not the first time people have tried to do something like this. But what everyone has done in the past is they have used the Cowling approximation. So fix the space-time, fix the gravity, perturb the matter, and you get something like this, which really doesn't coincide at all with our signal. But if you do the full treatment, we have found that you can explain very well this peak frequency. So I'm not an expert of LIGO data analysis, but it would be very interesting to find techniques able to recover this frequency evolution.
Is it easy to say why the Cowling approximation is failing here? Because, you know, if I just remember back to your density
Yes.
plots, it's not as if the, you know, distribution of matter inside the proto-neutron star looks like it's moving around a lot. It's not clear why the Calvin approximation would be poor here.
I'm not sure if there is an intuitive explanation, but it is known even even if you compute the F mode of a polytrope in GR, that if you do it in the Cowling approximation, you get a 50% difference from the non-Cowling approximation. I don't know whether there is an intuitive reason why there should be this difference.
Is it just because it's a low-order mode, low-order radial mode, and so the...
Yeah, this is a fundamental mode. So, oh, I see. Yes, this is a good point. So indeed, this is this mode is actually the fundamental mode. So there is no radial node.
So it's an F mode.
It's the F mode of the L equal 2, M equals 0.
Yeah.
So it's a quadrupolar mode. So this is very exciting for me because it opens a whole new possibility, which is to do astroseismology with neutron stars. Indeed, this frequency is very sensitive to the radius evolution of the proto-neutron star. Here we have done 2 simulations where we just changed a little bit one of the cross-section between neutrinos and matter. And it changes the radius of the proto-neutron star by, I don't know, it's hard to say, maybe ½ kilometer or so. But this leaves an imprint in the gravitational wave signal. At the same time, if we have information about neutrinos, neutrinos trace very well the accretion history of the proto-neutron star, because a large fraction of the electron-type neutrinos come from the accretion luminosity. So with combining these two, we'll have a way to track the radius and mass evolution of a hot proto-neutron star. So we'd be able to learn not only about the equation of state of cold nuclear matter, but also about neutrino-matter interactions, because this will tell us about the way in which the proto-neutron star shrinks as neutrinos escape from the very deep core. And perhaps this could allow us to confirm what we think is the explosion mechanism of core collapse supernovae. So I think I finally reached the conclusions. The main message that I want to give is that multi-messenger astronomy has really has opened really a lot of new opportunities, but also challenges. I think that there is merit in separately modeling gravitational waves, electromagnetic signals from these systems. But if we really want to do multi-messenger astrophysics, so combine all of the information together, we need models that can predict everything. And my main claim is that numerical relativity is a tool that can do that. I will not say that the simulations are already perfect and that we have everything under control, because this is not true. But we are getting there, and we are improving all the time. Thank you.
So where did the gamma rays come from in the numerical model?
Of the neutron star mesh? Oh, this is a challenging question. So in the simulations that I have done, I didn't include magnetic fields, so there is no gamma ray emission. There are some groups that have included magnetic fields, but only one group has been able to show, for example, the emergence of a jet in a merger simulation. So to answer briefly, the simulations cannot yet predict the gamma ray signal.
So does that imply a limit on what you can say about our process? You said there were 5 times as much that seemed to have come out versus what we'll see in the observation. In the simulations. So does that suggest that the late time behavior, which would depend on the magnetic field?
So what the Kir Anova observation suggests is that not all of the ejecta could have come from the dynamic ejection of material during merger. Because apart from Newtonian simulations, all GR simulations by all groups find that the amount of matter you can eject dynamically, so because of tides and shocks immediately at merger, is at most 1% of a solar mass. There is no model that can do more. It may be that you can increase it by, I don't know, having a phase transition in the equation of state when the 2 neutron stars touch. But most likely, the explanation is that much of this material comes from the evolution of the accretion disk left over afterwards. This is something that we cannot yet simulate safe consistently throughout the merger, because of the many time scales involved. But other groups have done simplified simulation where they start from an accretion disk, and they have shown that about 10% or more of the material can be unbound. A merger simulation find that the typical accretion disk mass is about 0.2 solar masses, unless you have these cases with prone collapse. So overall, the data seems to indicate that there is enough mass to explain the observation.
And regardless of where that stuff, how that stuff is removed, you do have this neutrino-driven wind coming off.
Yes.
Before whatever the late time behavior is. Right?
Yeah, the neutrino-driven wind will persist even at late times. Even if you form a black hole, there is, because of the geometry of the accretion disk, and because the accretion disk is semi-transparent to neutrinos, you naturally tend to focus neutrino radiation in the area on the pole of the black holes. So all of the material ejected there, independently of how it is ejected, is going to experience strong neutrino radiation. And unless it's being ejected at very large velocities, it will have its composition altered to a sufficient extent to make the blue Kir Anova counterpart.
So I'm wondering about the effects of magnetic fields on the equation. So at the moment you don't, similarly you don't have magnetic fields in your simulations.
Yes.
But it could have an effect on the equation of state, and I'm not even sure what direction it is. Because on the one hand, it could stabilize because it's another source of pressure, but on the other hand, it's another source of energy, so it adds on to the gravitating mass.
So just to give you an idea, in order for the pressure inside of a neutron star to change by 1%, you need to have a 10 to 17 Gauss field. So for the bulk of the neutron star, so during the in-spiral, for instance, unless you have enormous magnetic fields, they should not have any impact. After merger, magnetic fields are important because they enable all of these MHD instabilities and transport angular momentum. But otherwise, for the in-spiral part, they are not that important.